Hi everyone, in this video we're going to start chapter 3, which is titled Determinants, 3.1, an introduction to determinants. Okay, so in chapter 2, I believe it was section 2.2, we had a matrix A, B, C, D, and we computed this thing that was A times D minus B times C in finding the inverse of that matrix. And we stated that it could not be equal to 0 in order for the matrix to be invertible. We showed that back in 2.2. And if you read through it in the text, I don't think I mentioned it in the video actually, but if you read through it in the text, this is referred to as the determinant. The determinant, oh, I can spell today, D-E-T-R-M-I-N-A-N-T. There we go, of that matrix, okay? That's how you compute a determinant for a little 2x2 matrix. In 3.1, we're going to learn about and investigate what a determinant is, and then how do I find it in larger matrices. And what we're going to start with is a pretty gruesome computation where we're going to try to take this matrix A and reduce it using row operations, but keeping all of these A11, the little a's with subscripts in there. Okay, so the calculation is a little bit rough, but I think it's helpful to see ultimately where this calculation comes from. So I'm going to take my matrix A and scale rows 2 and 3 because, again, my goal is to reduce A into semi-echelon form, somewhat down into echelon form. And so we're going to take row 1, leave it the same. I'm going to give myself some space here. Okay, like I said, this calculation will get a little bit rough in the next and the following steps. All right, and row 2, I'm scaling by the factor A11, that top left entry. A11 times A21, A11, A22, and A11, A23. So I scaled row 2 by a factor of A11. And I'm doing the same thing in the bottom row, scaling that by a factor of A11, A31, A11, 32, A11, A33. Okay, so it got a little bit uglier. Now the next step in reducing this matrix is to use my leading entry, my top left A11, to eliminate everything that is below it. So if you want to pause the video, you can, and think about what you would need to do, what row operation would take that A11 and eliminate the entry below it. And if you figured it out, I'm not going to write it down, but I would multiply that A11 by the A21 that's below it. Well, negative A21 times the first row, add the second row, would eliminate the A11, A21. Actually, you know what? I will write that down. It's negative A21 times row 1, add row 2, store the result in row 2. Okay, if you want to grind through some ugly general calculation here, you absolutely can. If you want to pause the video, or I'll just write down what the result is, all right? And what we end up with across row 1, nothing happens. 1, 2, A1, 3. Going across row 2, if I perform that computation, I would get a 0 in that position. I would end up with, I'm going to switch the order and write the positive term first. A11, A22 minus A12, A21, okay? The A11, A22 is that guy right there. And the negative A12, A21, that was the scaling that I did in row 1. All right, now what I would end up in the last position is A11, A23 minus A13, A21. A21. Okay. Now the same idea can be applied to eliminate the A11, A31 in the bottom row. All right. That row operation is negative A31 times row 1. Add row 3. Store the result in row 3. I'm going to skip ahead to what that result would be now, but feel free to try it out on your own. Okay, and there we have the result in row 3. All right, that got a little ugly there, but let's keep going here and see what happens next. Now, if I'm going for echelon form here, right, let me go with green. I have my first pivot. I'm going to call that ugly mess my second pivot. So what would I do? I would use my second pivot to eliminate the entry that is below it. And I'm not going to go through this in crucial detail, but using the same strategy as the previous step of scaling and then performing my row operation. So I would scale by this factor and then do the row replacement operation. It gets real ugly. So feel free to just take my word for it on this one. And I'm just gonna skip ahead to the next the result of the next step. Okay, it would be a real big ugly mess, especially in video form, to try to walk you through it. But let's see what happens. A11, A12, A13. I'm going to rewrite the same row 2. 1, 1, 2, 2, A12, A21, 1, 1, 2, 3, A13, A21. Okay, and then what would happen now is the bottom row would become 0 here, 0 here, and then the last entry we're going to call A11 times this delta triangle, because delta triangle is really, really huge, okay? A lot of terms. And the reason we're going through it is it ultimately is where the formula for a determinant comes from, which is really cool, the way that we can like pull it apart. Okay, and so I'm going to skip ahead to what that delta triangle is. And there you have it. It's a giant collection of 6 terms, 3 positive, 3 negative, and really it's formed by row reduction, by reducing my matrix into echelon form. Okay, and if we're talking about invertible matrices and all that, that triangle, that has to be non-zero. That delta must be non-zero in order for my matrix to be invertible. And we're going to call delta the determinant of our 3 by 3 matrix. The determinant of the 3 by 3 matrix. Now, if we're defining that as the determinant, it would be pretty terrible to make you memorize that as a formula. So the next steps are how we can reorganize this into a much more familiar form that you may have seen in some course in the past, possibly in Calc 3. When you find cross products, you take determinants of 3 by 3 matrices. All right, so let me move this up a little bit. So here's what we're going to do. We're going to reorganize delta into a nicer form. And what I'm going to do is I'm going to start with my A11 terms, and I want to group them together and factor. A11 times the remaining terms in that, A22, A33, minus A11, oh, nope, that's the wrong subscripts, A23, A32. So that's our first grouping. And then we're going to group the next term a little bit differently. We're going to take our A12 terms, where are they? This one and this one, and factor out a negative A12 times A21 times A33, A23, A31. And then we're going to add to that we're going to take our A13 terms and factor them out. A13 times A21. Oops, that's a 2 and a 1. 3, 2 minus A22, A31. Now, if you're concerned about knowing like what all the subscripts are and where they came from, that's not like crucial at this point, because in one more step, this is going to take a much nicer form, and you'll see what I mean. All right, next step, let's see. So that triangle is now equal to, we're going to say this is A11. Now this, I want to write a little bit differently. I can take what I have in purple there and represent it as the determinant of a 2 by 2 matrix. This is A2, 2, A3, 3, A2, 3 is up there, and A3, 2 is over there. Okay, so if you think about how we compute determinants, this guy times this guy, let me circle them actually, it'll look cleaner. This times this minus that times that, right? That's how we compute 2 by 2 determinants. That's how we did it in chapter 2. It's how we'll do it moving forward. Okay, and I can do the same thing with the other two terms, but for the purposes of time, I'm going to jump right to the end of that. And there we have the formula for computing the determinant of a 3 by 3 matrix, our delta triangle there. We can write it even more in a more condensed way by saying A11, and then I'll explain what capital A11 is in a second, but it's the A11 times the determinant of capital A11 minus A12 times the determinant of capital A12 plus A13 times the determinant of capital A13. All right, and each of those capital AIJs, those AIJ is the submatrix formed by deleting row I and column J. So if you go back to my original matrix A to find the determinant, right, we're going to take this first entry, right, times the determinant of, now let's delete row I and column J, and that's the submatrix that remains. So A11 times that remaining submatrix, or the determinant of that remaining submatrix, and then you do the same thing for A12 times the determinant of delete this row, it's going to get messy, and this column, and I have that remaining submatrix, and then add to that A13, delete row 1 again, delete column 1, and now I have this remaining submatrix. And if you took Calc 3 before, or some other course, maybe a physics, where you found determinants of matrices, that's how you did it. But the reason why it works, sorry for the jumpiness there, is just stemming from row operations and our goal to be, for our matrix to be invertible. Now let's look at an example, and if you've seen it in another class, you probably know what you're doing here. But here's our matrix A, and we're going to find the determinant of A by going across row 1. The determinant of A is equal to my first entry, 1, times the determinant of this submatrix, 4, -1, -2, and 0. Then I'm going to say minus 5 times the determinant of this submatrix. There we go. Because I delete row 1, I delete column 1, and the submatrix that remains is 2, 0, -1, 0. And then let me change colors one more time. We'll have plus 0 times, and I'm still going to write it down even though I'm going to get a 0 here. 0 times the determinant of this submatrix, 2, 4, 0, -2. There we go, like that. Okay, finishing up the calculation, the determinant of A is equal to the determinant of my first submatrix. 4 times 0 is 0, minus -1 times -2 is -2. And then on the red part of the work there, I have inside of that determinant 2 times 0 minus -1 times 0 is going to give me 0 there, and then I get 0 there. So -2 is the actual completed determinant of A. I only got value out of that first submatrix. All right, in this slide, we've got a definition and a theorem. The definition of cofactor. Okay, so we define what a cofactor is. Given a matrix, the I comma j cofactor of A is the number C subscript ij given by this formula. And there's this -1 to the I plus j in that formula times the determinant of capital Aij. Okay, and then the theorem goes into the cofactor expansion of the determinant that you can go across any row or down any column to compute a determinant of a matrix. And that's really useful because it allows us to kind of search through our matrix and use rows of zeros, rows with lots of zeros, or columns with lots of zeros to compute our cofactor. And where that comes from is also kind of cool. In the big long triangle formula, if I had instead factored differently to get different terms out in front of each of those expressions, we could have organized it in a way that finds the determinant going down column 1 or going down column 3. Okay, and that's a useful tool to use in computing determinants by hand. One additional piece is this -1 to the I plus j. There was that one part of the factoring where I pulled a negative out in front, and that was so that my submatrix looked correct. All right, so that ultimately what that does is gives us a pattern for cofactor expansions. All right, and this pattern is something that you want to use if you're going along a different row or column, and it looks like this. So when we go along the first row, the terms in our cofactor expansion end up being positive, negative, positive, negative, positive, negative, etc. If you were expanding across row 2, it follows the opposite pattern: negative, positive, negative, positive, etc. Then to row 3, because the pattern continues downward: positive, negative, positive, negative, etc., 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 and it continues on in that fashion. Okay, so this is a really important pattern to know for our cofactor expansion if you're going along a different row or column. In this example, we are going to use that cofactor expansion and go across row 3 to find the determinant of A. All right, notice row 3 has a couple of zeros in it. Okay, so we'll take and write the determinant of A is equal to, I'm going to take this first entry, 0 times the determinant of, bracket, the submatrix formed by deleting that row and column, 5, 4, 0, -1. Okay, now that term, because of the pattern of my cofactor expansion, should be positive, and my next term should be negative. So minus, and I'm going to throw it in the parentheses, -2 times the determinant of, let's change colors so I can cross out another row and column. All right, so there is my submatrix, 1, 2, 0, -1. And then change colors one more time, and it'll be plus 0 times the determinant of, delete that row and that column, 1, 2, 5, 4. 1, 2, 5, and 4. And what we notice here, first part gives me 0, second part gives me 0. All that's left is -2, which is 2, times A times D, right there. 1 times -1 is -1, minus B times C, 2 times 0 is 0. Oops, that should be a parentheses. And multiply that out and you get -2. And so what we see there is you get the same determinant expanding along a different row, and you could pick any column you want, expand the determinant along that, and you'll get the exact same answer. So if we're picky about which row or column we use, we can often give ourselves less work. That is going to be really helpful in this example, because what we come across is a 1, 2, 3, 4, 5 by 5 matrix that we have to find the determinant of. And if we expanded this along row 1, say, right, we would have 3, right, times this submatrix that I'm circling here, minus -7 times this submatrix, plus 8 times that submatrix, minus 9 times that submatrix. It would be pretty intense. I think there would be, if the original is 5 by 5, yeah, there's going to be 5 terms that it expands out into. And then each of those involves a 4 by 4 determinant. So that'll expand out into 4 more 3 by 3 determinants. And if I'm losing you, that's okay. But what I'm saying is if we expand across row 1, it's going to be pretty killer to try to figure out the determinant. There will be tons and tons of computations involved in that, and it'll get really big and messy. On the other hand, if we expand our determinant along column 1, the determinant of A is equal to 3 times the determinant of, what's the submatrix that's left behind? It's this guy, 2 minus 5, 7, 3, 0, 1, 5, 0, 0, 2, 4, negative 1, 0, 0, negative 2, and 0. But are there any other terms? The answer is no, because each of the coefficients are 0. Oh, okay, so I want to look for columns of zeros when I'm finding determinants, or rows of zeros. Okay, so that made it much easier. Only one submatrix is remaining. So our next step is we're going to say 3 times, let's expand it along column 1 again, 2 times the determinant of some submatrix formed by deleting that and deleting that, 1, 5, 0, 2, 4, negative 1, 0, negative 2, 0. And that submatrix should look familiar. Its determinant is the one that we've already found twice in this section. So 3 times 2 times negative 2, which is negative 12. So we already got that determinant a couple times, so it stayed the same. All right, but the moral of the story is if you have lots of zeros, you use them to your advantage when you're doing determinants by hand. And as you might have wondered in the previous example, if there were only, if our matrix were triangular, so either zeros below the diagonal or all zeros above the diagonal, right, then what you end up with is the determinant of that matrix is the product of everything on the main diagonal. But you need entirely zeros below or entirely zeros above. All right, that is the end of this video. A little long on this one, I think, but thank you very much for sticking with me through it. Let me know if you have questions as you work through the homework section, and have a wonderful day. Thanks.